So now we will go to basics, really basics. We start from basics. These are the content of EE 124. Okay? So we have a structure here. This is MOS and PN. And we have both source and drain grounded. So this is source, this is drain, and this is gate. The main point is here. Do you see this? An insulator. So this forms a capacitor. Okay? Conducting metal, insulator, and then conducting region. We hope it to be conducting. Right? So this forms a capacitor. Now, so let's say it is at low voltage. We assume the threshold voltage is 0.7 volts. So it is like this. Right? What happened to the substrate? Because it's at low voltage, we can assume that this is like negative, right? So here you actually attract a lot of hole. And it is P-type anyway, right? And you are negative, right? 0 or negative, or below the threshold voltage, your hole tends to go to lower potential, right? So they got attract to the top. This is called accumulation. This is the regime called accumulation. Why? Because I accumulate a lot of hole on the top. Will I get any current? No, right? Because then I just like having a PNP, I mean back-to-back connected diode. This is N, this is P, this is N. So this is source, this is drain, this is the substrate. You're not going to get any current in this regime. Make sense? Now, I start increasing the voltage, VG becomes more positive. So if I positive here, then I try to repel away the hole. When I repel away the hole, I will get depletion region. Because in the substrate, it is P-type. Why you get P-type is because, remember the movie I just showed you? You might actually have a boron substituting the silicon, and then it becomes negative charge plus a hole. Right? This is the whole thing in the P substrate. Now, when you do a positive bias, you repel the hole away. As a result, you have this acceptor, which are ionized, left in this region. The main point is that these are immobile charge. Because they are the atom, you cannot move the atom in a crystal. Okay? Can I conduct any currents from source to drain in this case? I have N-type, I have negative region, I also have N-type. You cannot, because the middle one are immobile. Just imagine it's just like a water hose. On the left you have water, on the right you have water. In the middle you only have ice. They are frozen. So you cannot move them. So no water current. Just like here, no electron current, no electrical current. This region is called depletion. This region of operation. So we go from accumulation to depletion. Okay, so then let's work harder. I try to increase the gate voltage to be even more positive. What will happen? Now you will keep depleting more hole, but eventually it will also attract a lot of free electrons to the surface. This region is called inversion. Any idea why it is called inversion? Because originally, what was the type of the substrate? What was that? Is it N or P type? Original. P type. It has a lot of hole. But because I add a lot positive bias, then I induce a lot of electrons. Electrons are more than hole in this region. So it got inverted. Right? If we look at the band diagram, it will be even clearer why it is called inversion. Right? Can I conduct electrical current now? After inversion, does it conduct electrical current? From left to right? N-type, I have a lot of electron. At the channel, I have a lot of mobile electron. On the right, I have a lot of mobile electron. It becomes a conductor. And now I can start conducting current. Make sense? Any questions? Think about it. A few things not that important, but I want to mention why I don't keep depleting. And then instead of attracting electrons, it's just the electrostatics. And when you attract the electrons, the inversion layer, maybe I should use blue. The electron layer, inversion layer is just like the metal. It screens the electric field. Okay, it screens the E field, so you cannot further deplete. Instead, you will keep attracting more electron on the top. And what is threshold voltage? VTH. What did you learn about threshold voltage in the elementary class? What's the meaning of threshold voltage of a transistor? What is VTH? Do you remember? Okay. Can you say louder? Yeah, very good. You say, okay, like the turn on voltage of the transistor, right? We define as the threshold voltage is the VG. That is the voltage you are saying, right? After which the inversion layer is formed. Right? That is the threshold voltage. Once I form the inversion layer, what happened? Then it conducts. It conducts current. So threshold voltage is after which you start conducting. Okay? Now another important question. Okay, you start conducting, that is fine. But what happens if I keep increasing VG after threshold voltage? You will just attract more electrons, right? Due to Cox, due to the capacitor. So I did not make this very clear. This one is a capacitor, Cox. Based on this, you now should see that a transistor is a capacitively coupled device. We use the capacitor, the gate, insulator, and substrate, which form a capacitor, to change the carrier concentration under here. We use this capacitive coupling to control how much charge we have at the channel and the type of charge. When I keep increasing the voltage, then I will go from positive charge to negative charge and eventually mobile electron charge, so that I can conduct the current for MOS. Right, so if you forget and everything, you do need to remember what is a transistor. is a transfer resistor. You use the gate to conduct the conductivity. Think about, this is just a resistor from left to right. But its resistivity is controlled by this third terminal. That is the main point. It's a 3-terminal or 4-terminal, but the 3-terminal device. I use this one to control the conductivity of the channel, and then I form a transistor. Okay, this you must know, right? Otherwise, in the interview, how can you go through? Any questions? Okay. It's getting more and more messy, but we need to go through this review. Now then, I'm showing a band diagram. Anyone have not learned band diagram before? Have learned E221, or have you everyone taken E221? No. Are you from EE or then 128? Yeah, yeah. So you learn about this band diagram, right? Okay. So what are we looking at here? If I call this A dash, then this is what we are looking at. We have a transistor. It has oxide. This is the gate metal or gate poly. And then we have N plus. With N plus, this is source, this is drain, right? I keep repeating, right? Because I want you to know all these things. I'm cutting along this line. This is A dash, and this is A. Okay, I'm cutting vertically. Okay, so this is something you always need to ask yourself when you read paper or whatever. By the way, if you're interested, look at this book, free book published by Professor Chen Ming-Hu in Berkeley. He's the guru in this area. If you know that, he co-invented FinFET, right? There was a big deal 20 years ago or 25 years ago. And he has this book. You can take a look. It's free. He put it free on the website. I have the link here. Just review all this basic device physics, right? So this is the cut line. I already answered. This one, A dash. Now let's look at what happened. On the left, we have the gate. This is the gate. Here is the gate. And then at the middle, I have the oxide. And here is the substrate. Okay, I'm cutting from the gate through the oxide to the substrate and try to look at its band diagram. So the band diagram, we won't go into details, but the point is you have a conduction band, CB, a valence band, VB. Between the conduction band and valence band are the so-called forbidden gap. You cannot find any electron that has this energy. By the way, what is the units of band diagram? This direction is the energy, electron energy. It's telling you what is the electron energy if you are at those points. If the electrons at those points. Right? For example, if my electron is at this point, compared to electron at this point, these 2 points, their difference in energy is 3.1 eV. Again, what's EV? EV is the volt difference, what the energy gained by one electron when you travel across a potential difference of 1 volt. Right? So basically, it's saying that I have a 1 volt difference here, because we're talking about electron. So at the substrate, we have silicon, valence band and conduction band. The Fermi level is close to the valence band. So this is p-type, when the Fermi level is close to the valence band. And your electron cannot go through this barrier because you need very high energy, right? Under what condition I can go through this barrier? Under which condition? I just mentioned. If I want to go from here to here, I can never go from here to here classically. Huh? Tunneling? Tunneling, yeah? If you, yeah, very thin. When it is very thin, then you have tunneling. So gate current, this is one source of the gate current, what they call gate current. Again, this is capacitor. As I said earlier, this is capacitor. A good capacitor should not be leaky for DC current, right? But unfortunately, when this is very thin, I can have tunneling. So here basically give you the landscape of what an electron will see. For example, if the electron is here, right, I have an electron here. Then I see 3.1 eV of barrier, and then I will go to the other side. This is the gate. If I have a hole, the hole will reside on the valence band. Then in order to go through the barrier, I have 4.8 eV, even more difficult to go to the other side. Okay? What if this is a metal gate? This is polysilicon, that's why I still have E and EV and EC, right? So, what if it is a metal gate? Then you just replace it by a Fermi level. So this is still a substrate. You have conduction band, you have valence band, but here you will just replace by the Fermi level, EF, because it's metal. So here you have all the electron field, and above it, you will follow the Fermi-Dirac distribution, which we will discuss a little bit later. But it only has one level that you need to care about, right? And what is Fermi level, right? So what is Fermi level? But what is band gap first, right? It is easier to answer, right? Band gap, BG, equals to EC minus EV, right? So it is across which you cannot have the electron, right? The conduction band, this is the EC conduction band, and this is the EV. Actually, we already have EC and EV here. EC minus EV is the band gap. It's a gap. You do not allow electron to have energy at this level. Okay? Just physics, take it for granted. EF is at which you just fill up the electron to that place at absolute zero. So when you cool to very, very cold temperature, right, this is the at 0 Kelvin, which is impossible. It's not okay, right? It's 0 Kelvin. At 0 Kelvin, right? The EF, let me just say electron just occupy EF, right? Electron fills to EF. Okay? So what is the distribution probability, right? So now from the band diagram, of course, I already know if the electron is at this place, how much energy it has, right? But would the electron be everywhere? What's the probability? This is easy to understand. It's just like under the gravitational force, you have dust, right? A truss draw through, then you have lots of dust. You got lots of dust near to the ground, and you get fewer and fewer at the top, right? This is the Boltzmann distribution. For electron, it follows for high concentration, it follows the Fermi-Dirac distribution. The probability is F of E equals to 1 over exponential E minus EF divided by KT plus 1. That is the Fermi-Dirac distribution. We will discuss a little bit more, but I want you to appreciate that. For example, if I ask, what is the probability the electron is at this point, which is 3.1 plus even more, because 3E is this point minus EF, right? E minus EF, we need to know the distance. So this to here, let's say about 4 eV. Okay? But what is KT? KT is the thermal energy. What's the KT for room temperature? (26 millivolt). 4 divided by 26 millivolt. First of all, 4 divided by 20. Let's do approximation. 4 divided by 20 is what? 0.2. 0.4. Yeah, 0.2, right? 0.2, 4 divided by 20. But it's divided by 20 minutes, so I need to multiply by 1,000. So it's 200. What is exponential 200? I'm pretty sure Excel will say overflow. Very large. What is 1 over very large? Very small. So almost zero. You almost have no chance to find an electron to have this energy for this Fermi level. Right? So I want you to have this order of magnitude estimation skill, right? Think about this, okay? Now, so this tells us the probability. And this is the MOS Cap Band Diagram. Metal oxide semiconductor, because this is the gate, oxide, and substrate. Here is showing the band diagram. Right? You won't understand, if you have not learned this before, it's difficult to memorize right away, but you will keep referring to it. I hope you can all try to do this throughout this semester. Okay, so I already showed you the so-called flat band condition. You apply some gate voltage so that they are all flat. You see, this is flat. Okay, now we want to start asking, going back to here. We have tried to apply negative voltage, relative positive voltage, and very positive voltage, right? So what happened to the band diagram? So we have the so-called accumulation first. What is accumulation? Again, in a transistor, is it an off or on state? Off. For MOS, you apply negative bias, right? Now, this is something you need to remember. When I apply negative bias, the band diagram will go higher. Why is that? Because the band diagram, as I said, is the electron energy. You apply negative bias, electron energy increase because electron is negative charge. Okay, so this is a way I memorize it. So because of that, you're going to bend it. So what happened? You will get something like this. I will only talk about the metal gate. This is negative VG. Right? So because I apply negative VG, I push the gate up. Is that okay? I still keep the substrate at ground, but I apply negative VG. I push the gate up, which makes sense because the electron at the gate will feel the negative potential. So they should have a higher energy in this band diagram, because the band diagram is the electron energy. So you get this type of bending. Then I want to show the charge. What type of charge do you get on the left side for the gate? I've applied negative bias to it. You're going to put a lot of negative charge to it. This is Q. A lot of negative. Here I use arrow. It means a delta charge. Very narrow and very high. It's just like the metal. So if you have negative charge on one side of the capacitor, what happened to the other side? What charge do you get? It needs to be balanced, right? Positive. You will get very high positive charge here, which makes sense because now you see that the valence band is above the Fermi level, okay? Which you get a lot of holes. right? Does this make sense to you? Now then I start increasing the gate bias. I will go to the depletion region. So how should I draw the band diagram? When I start increasing, what happened to this part? Will you continue to go up or go down? I increase the voltage. Go down. Because this is the electron energy, right? If you have more positive, then your electron has less energy because electron is negative charge. So it will go down. I don't know how much it will go down, but let me just draw in this way. Too much? You might have something not good. I did not draw it proportionally. You bend in this way, and this is the Fermi level. Now, in this region, the Fermi level is inside the band gap. So you don't have much of hole and electron. On the other hand, you have the depletion charge. So now you are going to get, because you become more positive, so you're going to get positive charge on the one side, and you will get some negative depletion charge. But it is not a delta charge because it's spread out through some area, like what we are drawing, what we drew here. It has some depth. This is the depletion charge. Okay, and again, the depletion charge is fixed. You cannot move them. So as a result, it is still not conductive, right? Until finally we go to the what mode? Accumulation, depletion, and then what? Inversion. Yeah, inversion. Now you will see why inversion, right? So I keep more negative. Here I have larger electric field. And then I have something like this. This is EF. Now the EF is above the conduction band, right? So E minus EF is negative. So this term is small. This term gets larger, right? And if now you do this, I have more positive charge on the gate. I still have some depletion charge, but at the same time, I build up the electron, mobile electron. And these are what helping me to have conduction in the channel. Now, if now I say this is inversion, maybe you will feel better now even, right? Originally, this is P-type. The band diagram is bending upward. I keep increasing the gate voltage. Eventually, it's bending downward. It's like inverter. And at the same time, I'll say that you have hole at the beginning, and now you have a lot of electron at the surface. Any questions? Okay, so now we understand how to form the charge. Again, I want to remind you, this is, although equation, band theory are difficult, but there's one critical and easy thing you must know. What we are doing is that we're using the gauge through capacitive coupling to modulate the charge at the channel from hole to depletion layer to inversion layer. And so you have the charge. Now you form the charge, a good conductor. So what? Now you need to move them. You need to apply electric field so that they will move and becomes the current, right? It's just like allow a fill up the freeway with a lot of car. But if they are not moving, you don't have the flow of car. The freeway is not conducting. Okay? Now, so then now we need to come to an important concept is how fast does the electron move? Okay? And this is, so that is very important. We say the final current proportional to the velocity times the charge density. And we already derived the charge density in the previous slide. We know how you induce the charge already. How about the velocity? How does it work? Velocity comes from this. This is the velocity. It turned out to be something called mu times E, which is the mobility. Times the E field. Are you surprised with that? I say an electron moving at a velocity depending on the strength of the electric field. Does that make sense to you? Larger electric field, faster electron. This is not a tricky question. I'm not tricking you. Make sense? Yeah, larger electric field, I move faster, right? Make sense, right? But however, this is not always true. If we try to plot the E field as the x-axis and the velocity on the y-axis, we do see a straight line at the beginning, but then it saturates. Okay, so the first part, it does has a slope of mu, which means V equals to mu times E. So if I increase the electric field, my electron will move faster. However, eventually, after a critical field, let me just call it E critical, the velocity does not increase anymore. This is the so-called saturation velocity. Is that okay? That's all I want to say. You increase the electric field, your electron move faster. Even higher electric field move even faster. But eventually, it will just saturate at a certain velocity. Okay? Now, different material has different V versus E characteristic. For silicon, it's pretty much like what I said. At the beginning, you increase electric field, the velocity will increase, eventually it saturates. For some special material like gallium arsenide that you use a lot in RF, it increases, but then it can decrease. That is due to the band structure, because they have so-called light electron or heavy electron. So this is a little bit profound, right? We won't discuss. It's just like at the beginning, they populate the valley. Most of them are light electrons, so they move very fast. But when gain enough energy, they got scattered to the heavy valley, so become heavy. They become heavy, so they move slow. And that's why you have this negative differential curve. Okay? But no worry about this. We will discuss a little bit more later. But at this point, remember, velocity is proportional to mobility times electric field. And eventually it saturates at saturation velocity. Okay? This is easy to understand. Think about, it's not exactly the same, but think about you drop a ball from the aeroplane, right? At the beginning, you keep increasing, and eventually it will saturate at a constant speed. It won't increase forever, because the faster you move, the more friction you get. And that is actually almost the case for the saturation. The faster you move, the more mechanism you can lose your energy. They call optical photon, you get excited, you keep losing energy. So that's why you cannot keep gaining energy. Cannot gain any velocity. Okay, good. So now we have the velocity, we have the charge. Then we are almost ready to derive the currents for transistor, right? But before that, we need to understand what happened to the electric field or the potential along the channel. So again, right, we keep repeating, which is good. This is what? This is a capacitor, COS. Remember, right? Sometimes it's silicon dioxide or hafnium dioxide. We just introduced high K dielectric, right? Now, then this is the gate, right? So my question here is, what is the potential along this channel? Okay, so I call this X equal to 0, and here X equal to L. L is the length of my transistor, right? What is the potential? So I try to ask you to sketch V of X as a function of L. Okay, start from 0. No, as a function of X. Right? But up to L. Can you tell me at 0, at this point, what potential it is based on the connection? At this point. Well, it is connected to 0, right? Then of course at this point it is 0. How about at this point? What is the potential? Huh? Just say it, be brave. 1. It's just the VD, right? Because I apply 1 volt to here. So it will increase, but it might not increase linearly, so we will just write it in this way. Okay? So at this point it is 0, and at this point is VD. Make sense? This is kind of common sense, right? You start from 0 and then you reach 1 volt. Whether it's a straight line, we don't know. We need to solve the Poisson equation. Many things need to solve. But at least I know it is increasing. Okay? Then I ask you to do a second plot. This plot is also easy. Instead of plotting Vx, I want you to plot Vg minus V of x. What is Vg here? 5. It's given 5 volt. So when x equal to 0, Vx equals to 0. So I start with 5 volts. Vg minus Vx. When I reach L, then it will drop to what? It was 1 volt there, right? So Vg minus Vx is equal to 5 minus 4 equal, 5 minus 1 equals to 4 volt. Okay, that's it, right? Very simple. Why I want to draw this? I want you to realize that, hey, you're going from left to right is a transistor, but the potential difference between the gates and the channel is changing. It was large at the source and becomes smaller at the drain. Okay, so do not think of transistor as a single point. It's a continuous region, right? Like a waterfall or a river. Right? On the left, it is 5 on the potential difference. So what I'm trying to say is this, right? This is 5, this is 0, and this is 5, and this is 4. And you are applying this across a capacitor. This one, COS, right? So I have, look at this. They are all capacitor. Right? The capacitor on the left, it has 5 and 0 difference. The capacitor, this is 1, not 4, sorry. The capacitor on the right is 1 and 5 difference, right? Smaller potential difference on the drain side. Make sense? Any questions? Why do I want to do this? Then in principle, I can find out the amount of charge it has. What is the charge across a capacitor? is the capacitance times the potential difference. Do you agree with the equation I wrote down? Q over V equal to C. Q over delta V equal to C. That is the definition, right, of capacitor. So what I'm saying that the charge across this capacitor is equal to Cox times Vg minus Vx. Okay? But the point is Vx is different at every point. So I cannot say that this is the overall. I can only say that at x equal to this point, how much charge I have. You see, I try to keep a space. That is because the charge I'm interested in is not the total charge, but the free electron. What I care about is the free electron, because only free electron contributes to the total current. So free electrons does not form until you reach the threshold voltage. Look at this, right? Until you reach threshold voltage, before you reach the threshold voltage, you don't have free electron. Only after that you have. You do have a lot of charge already, but they are immobile. Or like this band diagram, I start with a lot of immobile depletion charge. Only after inversion will I get some free electron, right? So if I care about the free electron only, then I need to subtract this one by the VTH, threshold voltage, which makes sense. If the potential difference across it is equal to VTH, then I just have no free electron, right? So from here, I get the charge. I also know the velocity V equals to the mobility times the electric field, which is equal to, we discussed yesterday already, dV dx. dV dx, negative dV dx is the electric field, right? Potential difference. Then you solve it. We are not going to solve it. You don't need to solve it. I just want to remind you why this quantity are important. The result is you know that the current must be equal to the unit of charge times the width of the transistor times the velocity times the charge density, right? This is the free electron. You go through the solving process, do some integration. What you get is W on L mu Cox times VGS minus VTH times VDS minus VDS squared over 2. Make sense? Current depends on W, of course. Why the transistor, right? So, but what is W here? Do you know? It's talking about the width. If we try to look at 3 dimension, right? So this is the W into the screen, the width of the transistor. What we are seeing here is the length of the transistor. Okay? So we're done with the so-called linear mode, right? Let's go to see what happened to pinch off. So what I'm going to do is that I will start increasing. First of all, I assume the threshold voltage is 1 volt. And at the beginning, right, I have the gate at 2 volts. Of this is at 0 volt. And then we start with drain at 0.5 volt. How much charge do I have under here? Q equals to Cox times 2 minus 0 minus 1, which is equal to Cox. The charge under here I just told you what is the charge. Vg minus Vx minus Vth times Cox is the charge density you get. Vg is 2. The channel potential is 0. Threshold voltage is 1. That's why I get 1 Cox units of charge here. Now then I try to look at the charge here. What do I get? Cox times Vg is 2, but now it is 0.5 at the channel, and this is 1, so I only get 0.5 Cox. Make sense? The main point is because my channel potential keep increasing from left to right, and as a result, the charge I can reduce is less. Okay? And then the next thing is that what if I increase this to 1 volt instead? Okay, I still have the gate at 2 volts, source at 0 volt, but now drain is at 1 volt. Well, on the left it's still the same because there's no difference, so it is still 1 Cox, but on the right, this point, Cox at this point, right? Q equals to Cox times 2 minus what? What is the channel potential at this point? What is the channel potential at this point? Say again. Can you say it's 1? And then the Vth is also 1, right? So this gives me 0. I don't have any charge on the right. And that is called pinch off. Now this is interesting, right? So for a transistor, if you change the gate voltage, you actually get the drain voltage, you get much less charge in the other region. Okay? So this is the summary. If we keep increasing the Vd, right, eventually you have pinch off. The reason is Vg or Cox times Vg minus V at L minus Vth equals to 0. In other words, this is Vd. So in other words, it means Vd equals to Vg minus Vth. When Vd equal to Vg minus Vth, you run into this pinch off region. If in the last figure, if I keep increasing Vd, what happened? The pinch off point will shift to the left, so that in this case, right, it's better to do. So that in this case, Vg minus VL1 is actually equals to Vth. Just pinch off. It pinch off earlier. So you have a longer pinch off region. Okay? And we define something called Vset equal to Vgs minus Vth, which will be used later. Okay? So because of time, I will stop here, but let me know if you have any questions.